Good afternoon, everyone. It is lovely to see all of you today. And I know that there are a few faces we're missing. I perhaps would put this down to some MSTs. But regardless, stay involved. Keep doing your grok exercises because we are roughly halfway through semester. And with that should also come an opportunity in 1 week's time for you to sit back and take a bit of a break, not think about algorithms too much for a week, and enjoy a bit of time off. If you remember yesterday, we were looking at Quicksort. This was our new algorithm that we learned that could sort in average case n log n time. There were a few little caveats to this, and one thing that particularly tripped us up was the selection of the pivot, that is, which element we were going to use at each recursive call to compare all other elements to, and also our runtime analysis was somewhat tricky. Along with this, we spent quite a bit of time on the partition function, which was really the complex element of Quicksort to code. Without the partition function, the code of Quicksort was relatively simple. We're going to look at one other way of doing the partitioning today. Recall our Quicksort code just had these two recursive, it had our partition function that we would call first, and once we were partitioned, the only thing we needed to do to continue our quicksort was to recurse on the left side of the array, the smaller side than the pivot, and on the right side, the larger elements of the pivot. But in order to explain this different partitioning function, I actually thought that we might do some interpretive dance. In this class, we've already had song, we've had presidential speeches, we've had a whole lot of fun. So I thought, you know, the only element missing is dance. And what better dance than Hungarian folk dance? So I present to you the Hungarian Quicksort dances. We'll do a bit of a step through of the algorithm while our beautiful Hungarian dancers are doing it for us. You see, number 3 on the far side is going to be our pivot. On the other side, we have a sequence of elements, each of which are comparing themselves to the pivot. What we're looking for is an element that is smaller than 3. That is, it needs to be moved to the other side for our partition function. Is 5 bigger than 3? Yes, 5 is still bigger than 3, so we don't need to do anything. We don't need to swap anything. What about 2? Is 2 bigger than 3? No, 2 is smaller. So watch what we do. Do a little hop and clap, and switch the 2 into the first place. Now 2 passes the hat on to the next element along. And we're going to start comparing from the opposite end. So is 0 smaller than 3? Yes. Is 1 smaller than 3? Yes. Is 8 smaller than 3? No. So we have an inversion. That is the side that it doesn't match the side we're comparing from. So what we do our little hop and clap thing, and we switch it out to the end. Now we continue this process. Is 7 as compared to 3 an inversion? Is it on the right side? It's on the right side. Great. So now we have completed our first partition. After we partition, we have our 2 recursive calls Quicksort. There is our recursive call for the small side, and that's the one we're going to start with. We've chosen our new pivot, that's 2. Is 1 on the right side of 2? No, it isn't. We do our switch. Is 0 on the right side of 2? Yes, it is. And now if you'll notice, we have no recursive call on the right side of this little group of 3. So now we move to the left side. Those 2 are in inversion, so we swap. I jumped early. We're still finishing off those ones. Now our whole right side of the array is sorted, the smaller side, and now we move to the left side. There we go. 7 is our new pivot and is comparing with the end of the larger side. A 7 and 6 an inversion? Yes, they are. So we swap it over. Now we compare with 8. Is 8 larger than 7? It's on the wrong side, so we have another inversion. Hopefully now you should start to get the pattern. 7 and 9 inversion. No, 9 is on the right side. But when we get to 4, the next one, we'll have to swap that with the pivot. Because 4 is smaller than 7. And I think that should be enough of an illustration of this alternate version of the partition function for all of you. I'm not the first person to do these Hungarian folk dances. These have been a mainstay of algorithmic education for a long time. And if you want to study any of the sorting algorithms that we've covered in this class, all of them are available on YouTube. Search sorting Hungarian folk dance and then the name of the algorithm, and you'll be able to watch a video of the dancers going ahead and acting out the algorithm that may help you to get a bit of an intuition and a sense for how these algorithms play out. I personally found it very helpful and entertaining when learning these algorithms, and hopefully you will too. But now back to our pivot selection. If we select a pivot with a random permutation of our array elements, the math is going to get quite hard. We didn't even go through it other than to note that approximately you get 1.44 n log n plus O of n, which is of course n log n. But this was very difficult to compute, and so we need perhaps a better strategy for performing our analysis of the time efficiency of Quicksort. We also note that arrays are generally not entirely random. It's frequent when you're sorting real data to come across sorted data that you then have to check if it's sorted, or reverse sorted data. And if you run Quicksort on these, depending on your choice of your pivot element, you'll actually get to the worst case. The worst case was when our recursive function only recurses on the same size of the problem -1. So if we had 9 elements, we could get a recursive call, 2 recursive calls, one of which is a recursive call on size 0, so there are no elements on one side of the pivot, and then the recursive call on the other side would be 8 elements. And if we keep doing this, we get n squared. And this could happen in the case of a sorted array. And given that sorted arrays are really common in the wild and for many types of data that you might actually be running your sorting algorithm on, we should probably find a better way of selecting our pivot than just choosing the first element. We could choose the midpoint as the pivot, but this also turns out to be relatively hard to analyze and doesn't necessarily give us what we're looking for in terms of operating well in all our different conditions. We could also be pretty fancy and choose the median value, that is the middle value of the start, the middle, and the end of the array, or some strategy based on medians. But there's a solution to this. Some clever chap figured out that you can pick a random element as your pivot, and this makes the analysis much, much easier and also gives you a bit of a hedging effect against encountering an already sorted or a reverse sorted array. Now the input sequence doesn't matter for our analysis because the randomization element, when we're trying to figure out the average case, is taken care of by the randomization of the selection of our pivot point. This gives us an expected runtime of always n log n. Now this doesn't mean on every single input, every single time you will get n log n. Why is this? Well, let's say we do encounter a sorted array and we do still randomly pick this time the very first element to be the pivot, we'll still get an n squared runtime on that particular input. However, the important thing here is that our average case, normally when we run the algorithm, we expect it to run an n log n time, and that's generally what we're looking for. In fact, you can always find, if you know how someone is going to pick their pivot, and the sorting algorithm that they're going to use, you can pick an adversarial input. That is, you can pick an array that you know is specifically designed to run badly on their selection of pivot and on their selection of algorithm. This is why we tend to focus on the average case, but also include an analysis of both the best case, which you'd be very lucky to find, and the worst case, which can occur both in nature and in adversarial situations. Now we're finally ready to take a look at quicksort.c, the actual code for... We have our quicksort function that is almost identical to the pseudocode at which we were looking before. We have new variables here for first equal and first greater. These are going to be marking off which sides are already partitioned and therefore what are the boundaries at which we have to recurse. We choose a pivot. In this case, unlike the pseudocode we originally showed, we're going to allow different mechanisms to choose the pivot, so you can swap this function in and out simply. We then call our partition function, call quicksort twice, and we're done. I would strongly encourage you to actually have a go at writing quicksort because of its simplicity. This particular portion of it, the main quicksort function itself, should really not take you very long. Of course, the bugbear exists when you get to the partition function, but there are also simple versions of this available online for you to compare and contrast to that will enable you to get a feel for what's actually happening in quicksort. In this case, we're using the original quicksort method that we discussed in yesterday's lecture. That was we were choosing the pivot at the start and then going along a single direction, comparing everything with our pivot and making swaps as appropriate. Another feature of the code here is using our compare function that we also showed off yesterday. Remember, when implemented, this was just taking the difference between two elements and determining whether the difference was positive, negative, or zero. If it was positive, the first element was larger than the second. If it was zero, the two elements were equal. And then if it was negative, then the second element was larger than the first. And this allows us to determine whether the element we're looking at is bigger than the pivot, equal to the pivot, or smaller than the pivot. I'm not going to belabor the details here because we've already stepped through quicksort in quite some detail in pseudocode, but it is striking quite how similar this implementation is to what we've already looked at. In here we have three different versions of our choose_pivot function, and we're actually going to look at these pretty quickly and comment out the three different lines. So this is not very useful C, as many of you would notice. As soon as you run this function, it will reach the first line and return immediately. But the reason we've written it in here is so we can simply comment out one of the lines and see how long our quicksort takes on the other pivots. We have a main function that is a simple driver, where n is going to give us the size of the array that we're sorting. So let's give this a run on a few different inputs. Compile it as always. And I think I left this one uncommented. Yes. So the first pivot selection technique that we're using is the random selection of a pivot. And let's look here how many different comparisons we did. So looking at random items, we did on average 20.7 comparisons per item and 63.2 copies per item. That means copying things to different places in the array. When we copy, that means we have to do one of the swaps. We're moving things around, and that takes some of the computer's time. You can see that this isn't very different from what would happen if we ran it on a sorted array, a reverse sorted array, or the only difference is if all the items are uniform. If all the items in the array are the same, we only do one comparison per item and we don't have to do any swaps because the array is already sorted. Now let's try run it with choosing the middle element. Let's see what happens. Maybe I'll move this up a little so that we can compare it against the other version of quicksort. Now you can see for sorted, we've actually done a little better here. It only takes us 16.5 comparisons per item as opposed to 21.2 there, and fewer copies. The same for reverse sorted, the same for uniform, and for random items, it's done mostly equivalent. Let's run it again and see what happens. No change, as we would expect. But if I rerun the random one, it's possible we will get slightly different those values a little different to the ones we got above. 21.2, 21.2. Curious. Now let's try it with choosing the pivot as the first element. Now you can see that when we run Quicksort, it's taking quite some time to do this 318.8 per item. Wow, that's a huge difference from our other two pivot selection methods. So even while Quicksort on an average case basis can be pretty good even with choosing the pivot as the first item, when we encounter real data in the wild, and we expect that to sometimes come in sorted form, choosing the first element of a pivot actually performs pretty badly. Now, for a reverse sorted array, this is taking even longer. Let's give it another 20 seconds or so and see if it finishes. I have a feeling it might not. Every year, the computers we do this on get a little faster, so you never know if one year it's actually going to finish. Okay, we'll leave that running and maybe come back to it when it's done. Our message here is the importance of the best, worst case, and average analysis, and how each of these play a different role when we're deciding which algorithms to use. Even more than that, we can go beyond best case, worst case, and average case analysis and actually figure out how our algorithm is going to run on real data. And this is where, again, your job as algorithmic designers and engineers gets to be quite interesting. Best case is often silly because it very rarely happens. So be very, very careful in choosing an algorithm that performs exceptionally well on best case but doesn't actually perform very well on average case or on your real data. With average case, we're really relying on the randomness of our input data. So if it turns out that the distribution that our algorithm is going to run on really is random, then we've probably made a pretty good selection by choosing an algorithm that is average case good. This is because the average case analyses rely on an even probability distribution across all the different possibilities for your data. But some real world data isn't actually randomized or might be skewed in terms of its probability distribution. So average case isn't always going to give us an indication of what's going on. Worst case is pretty safe, but again, maybe sometimes we can take advantage of the fact that our data is non-uniform in probability and actually write an algorithm that in the real world performs better despite our analysis. We've looked at optimizing algorithms for best case, worst case, and average case, but it's time to look at what would happen if we tried to optimize an algorithm in the real world. The algorithm we're going to look at is one that many of you have hopefully already seen in this class and maybe in other instances, and it's one that I've actually encountered numerous times when I was an undergraduate student interviewing for internships.
The human X chromosome contains hundreds of genes associated with a wide range of diseases, including hemophilia and red-green color blindness. An interesting aspect of the X chromosome is its inheritance pattern. Unlike the Y chromosome, where the number of possible ancestors must be equal to the number of generations, or the 22 other autosomes, where the maximum number of possible ancestors is equal to 2 to the power of the number of generations, X chromosome inheritance is a little more complicated. A male will inherit one of 2 possible X chromosomes from his mother, either from his maternal grandmother or his maternal grandfather. A female will also inherit one X chromosome from her father, introducing an asymmetry in the number of possible ancestors. Turns out there's an efficient way to calculate the number of possible X chromosome ancestors using the Fibonacci sequence. For a male, the number of possible ancestors is equal to the nth Fibonacci number, where n is equal to the number of generations going back. For females, this method can also be used, but n is equal to the number of generations plus 1.
This is, of course, the program that asks you to generate the nth Fibonacci number. Now, if any of you have your laptops and are playing along at home, I would encourage you right now to tap out the simplest version of Fibonacci that you can. Just the one-line return statement. If you can write it down right now, I'll give you 30 seconds to write down a function that computes the nth Fibonacci number. Okay, with everyone done, I would like to invite one of our guests to the class today to give us some helpful feedback about how we might calculate the nth Fibonacci number. Want to remind us of your name? Angela. So Angela, how would we calculate the nth Fibonacci number?
Using the fact that, like, if we say fn equals to choose the function to calculate the number, you're going to say fn equals to fn minus 1 times n.
Fn minus 1 plus f of n minus...
Oh, sorry, wait.
Fibonacci sequence is the sum of the two prior Fibonacci numbers.
N minus 2 plus fn minus 1 plus n.
Oh, that's it? No, just fn minus 1 plus fn minus 2. I'm glad you came back for some revision. Angela is doing DOA this semester and so has come back to brush up on some skills and hang out with our lovely third row crew. Okay, so that's our simplest version, is this recursive algorithm. We have our base case, so we know the Fibonacci sequence starts 1, 1, 2, 3, 5, 8, 1, 3, or 13. And so we can write in our base case and then recursively compute the nth Fibonacci number. Let's go to our actual implementation. Oh my God, this still hasn't finished. Would you look at that? Reverse sorted is still running. Well, I think it's time to terminate it and move on. I certainly don't have time to wait for it, and I don't think any of you do either. So let's move to our Fibonacci code and check out the first one. And I assure you, by the end of this lecture, you will wish you had never seen the Fibonacci sequence at all. Here we are, Fibonacci 1. Which Fibonacci number do you want to calculate? The main function just gives us the result. One thing to note here is I'm using long type. This is an expanded version of an expanded version of an integer. So a long is an integer that is 64 bits in length at least on most systems, and a long is even longer than that. It's implementation dependent, but it's the longest we can get in C. I don't think there's a long, or a long, or a long. But if there is, feel free to let me know. Anyway, so we have our simple Fibonacci code. If n is less than or equal to 1, that's our base case to our recursive call, return 1. And otherwise, as Angela so beautifully pointed out to us, it is the sum of the prior two Fibonacci numbers. So let's give this a run and see how high we can get. So clang, fib1. Which Fibonacci number do you want to calculate? It'll work pretty well for smaller numbers. That was the fifth Fibonacci number. Again, depending on how you define the Fibonacci sequence, you'll either start it at 0 or start it at 1. We don't really care about that. We just want to know that our Fibonacci number program will run for pretty high numbers. Ooh, that's not going so fast. That 1000th Fibonacci number is taking a while. Doesn't seem very efficient. Perhaps the reason it's inefficient is because we're doing two recursive calls and actually reusing all this work. So let's say we want to calculate the 13th Fibonacci number. We would do Fibonacci of 11 twice, because we would do it once for Fibonacci of 12, and then Fibonacci of 12 would do Fibonacci of 11, and then we'd also do it another time because we'd call it from fib of n minus 2. And so there's going to be a lot of wasted work, and the runtime of this is really inefficient. Another reason why many of you would care about the efficiency of these programs is because when you do programming interviews for your industry jobs that some of you might go to, you'll be asked to iterate and improve on your algorithm. They'll say, here's a problem, here's the specification of it, write an algorithm that solves it for me. Then they'll say, can you point out why your algorithm might not be so efficient? And then the more important question, can you find a way to improve it? So that's what we're going to do right now. For the algorithm that we just wrote, we have exponential time to calculate the nth Fibonacci number. It's O of 1.7 to the n, but the advantage being is that many of you were able to code it in just a few seconds. Can we do better? The answer in this class is almost always yes. Implementation number 2 takes advantage of the fact that we were just talking about that we're doing a lot of redundant work. Well, the redundant work is the same every time, so what if we had a way of the computer remembering what the prior work that it had done was and then reusing it? This we call memoization, and it's another important technique in algorithmic design. Not one that we'll encounter many times in this semester, but as you go forward in your computer science education, you'll encounter it again and again as a way to make algorithmic improvements and optimizations to your code. Fib2 is going to have runtime O of n, but like we talked about in our very first week, there's going to be a trade-off. In order to remember what we've done before, that's going to consume some of the computer's memory. And so if we store n-1, n-2, n-3, n-4 in memory so that we don't have to reuse them, that's going to take up O of n memory. It's still running. So let's check out our code for Fib2. Here is our code for Fib2. It is substantially longer than Fib1. And this time, I'm using a trick. I'm using unsigned long longs. The reason I'm doing this is because unsigned long longs, remember, if we have signed integers, we're only using half of the clock, half of the memory to store our positive numbers. But because Fibonacci numbers are all positive, I can say, well, let's ignore the negative numbers and just make all the memory dedicated to storing positive numbers. So if I add unsigned, I can get double the space. Great. I am going to create an array n, which will store the prior results of smaller Fibonacci numbers. So for example, the first time that we call fib of 11, we will store the result of fib 11 in the array, and then the next time that fib of 11 gets called, instead of making two recursive calls, we'll just go back to the array and see what the value was. I am using one or two little functions here to dynamically size the array. Don't worry about these for the moment. They're extraneous details for our purposes. What matters is when we actually call our Fibonacci function, the first thing we do is if the Fibonacci number is not our base case, we check if the value in the array for the nth Fibonacci number is already set. So we are going to store the nth Fibonacci number in our memory array at position n. If the position is not empty, what am I doing here? I'm not sure. We're going to move on. I'll figure out what I was doing there later. Otherwise, if n equals 1, make sure to, that's our base case, set the base case. If the memory is unpopulated and we are, oh, this was n is less than 0, that's why. For n is less than 0, we should not reach that branch, and because there are no Fibonacci numbers less than 0. But if it's equal to 0, we're just going to mark the 0th position in the array as 0. That's what we're doing there. So really, we could have hopefully done that and it would have worked still. Anyway, moving on. If we're at 1, again, we store a 1 in the array. That's a base case. And now we finally go to the recursive call. We check if the element in the array corresponding to the nth minus 1 Fibonacci number is present. If it's present, we can just read it out and use it when we get to our return call at the bottom. So that's going to be our variable n minus 1. If it's not present, we actually need to go ahead and calculate it. If it's not present, we go ahead and do our recursive call. When our recursive call is finished, we then save the result of the recursive call into our memory, into what's keeping track of all the prior calls, so that we don't have to go back and do it again. We do the same thing for the nth minus 2 Fibonacci number. We check in the memory and just access it out. Now, why might we, oh, here we go, and then we do it there. Now, what I'm doing here is just making sure to see that we don't have an integer overflow, and rather than int max, which you have seen in your earlier examples, we're using long underscore max. This is the same as int max, just for long longs, and I think maybe there's an unsigned long max. Maybe there's an error in this code, but I'll have to check that out after. Anyway, it's not particularly relevant to the success of our algorithm. Let's run fib2 on 5. That was near instant. Probably couldn't tell much difference from the prior one because the other one seemed pretty fast on 5 as well. But let's see what happens if we do it on 1,000. Oh, The 1000th Fibonacci number is too long, but at least it gave us an answer pretty quickly. What about with the 15th Fibonacci number? Oh. 15th Fibonacci number came out super quickly. How would it work if we did that on Fib 1? Took considerably longer. Let's do Fib 20. Fib 20 takes ages on that one. And with Fib 2, near instant. So you can see there's already a pretty significant difference between the two, and as our Fibonacci numbers get larger and larger, the difference becomes more and more pronounced, because remember from Liam's mutiny the other day, we have two functions competing with each other, and pretty soon the exponential function, that's 1.7 to the n that was Fib 1's runtime, gets much, 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 much bigger than O of n really, really quickly, and that difference becomes more pronounced the larger that n gets. So we've done our memoization, but we can still probably do better. We now have implementation 3. Implementation 3 has runtime O of n, but stores a constant number of values in memory. This is because we are no longer using a recursive version of the Fibonacci algorithm. This is actually fairly simple. It's just a standard for loop. And still produces the correct answer. So what you've been taught all along was a lie. The recursive version of the Fibonacci algorithm is probably not one that anyone should use, because this is much more efficient. Let's check out Fib 3. There's our Fib 3.
This should be familiar because it's an exercising grok.
Grok's stealing my exercises. Let's calculate the 20th one. That ran pretty fast too. Let's see if we can get it to a point where it'll... Okay, 30's fast and 40's fast. And we probably won't see much of a difference with Fib 2. Because both of them run in O of n time. In this case, the difference is the amount of storage they use. However, one thing to remember that we talked about in our week on memory is that our memory is bounded. So if we're using an algorithm that takes O of n memory and it's recursive, well, eventually we might just create too many stack frames. We'll have too many nested functions, too many nested recursive calls, and when we run out of the room, we'll get a stack overflow, we might get, and the program will terminate and it won't keep running. So the iterative version has multiple advantages over the recursive version, even with memoization. What if we want to run the program 1,000,000 times? We're going to be running this over and over and over again, and each time we're replicating the work. So surely there is a better way of doing this. Well, we could choose Fib2 and cache the results in a file. Instead of having a variable in the memory of the program, if every time we ran the program, we instead stored the output from prior versions, when we came to run the program again, we'd save ourselves a lot of work. In this case, we'd get an advantage over even Fib3 in terms of the runtime, because Fib3 would have to do the same number of iterations each time, but if we chose Fib2 and instead saved like Fib_n-1 and Fib_n-2 to a file, when it came time to calculate Fib of n again, we'd just have to read that file back, read the last entries, and sum them back together. Now, those of you who are paying particularly close attention might ask, well, how many things are you going to have in a file? Won't it take a while for you to read the file out? Won't that take O of n time and O of n space? Yes, and when it comes down to actually deciding which of these algorithms to use at the end of the day and how to cache things, this is going to come down to a lot of the details about your specific use case. You could go one step further with this, and instead of writing it out to a file, you could actually store it in a program that's always running on the computer. If you are Facebook and you want to see which users are logged in at any given time, you don't want to have to go back to your database, to the big file stored on the computer, to see when users logged in. Instead, you store all the users who've recently been logged in and their details inside the computer's memory and leave that computer running. Then when you have your program that needs to figure out who's logged in, you go and look at the computer's memory and don't have to read all the file back. we can do the same kind of thing if we're computing Fibonacci numbers over and over and over again, which perhaps we might be doing if we're in this kind of genetics context, or perhaps something else that's a little less contrived. If we store the results in memory, we can cache them. This is called caching, to store them on a temporary basis somewhere in memory and access them really, really quickly, and thereby perform our million computations very, very fast. But what about if we want to run it not just many, many times, but let's switch to trying to run it with really big numbers. We saw that we got an overflow when I tried fib of 1,000. Our programs aren't really going to work for, fib1 and fib2 aren't going to work for really large numbers because we'll get a stack overflow. And even fib3 is going to be bounded by the size of unsigned long longs. So if we want to run it with really, really big numbers, we're no longer going to be able to use C's built-in types. We're going to need to create a new custom type in C that figures out a way to combine individual integers and chain them together to create even big numbers. Just like we saw with our clocks, if one clock doesn't have enough numbers for you to store the number that you're thinking of, you might combine two different clocks and read them off together. And this is the idea behind big nums, which is what Python behind the scenes is using to allow you to manipulate really big numbers. However, unfortunately, when we deal with big nums, we do get a problem where our operations are no longer constant time. So just as we said, when you add two numbers together, if you're figuring out how many operations that is, that should just be a single operation. When you're working with big nums, that's no longer true because you might have to do multiple comparisons and multiple operations in order to do a single normal arithmetic operation. But at the bottom of this slide, we have a solution to some of our challenges. We have a formula called Binet's formula. And this is where we start to get really clever for your programming interviews. If you can whip out off the top of your head or from your notepad fib1, fib2, and fib3, and then impress your interviewer with this, I can almost guarantee you that you will get a raise of eyebrows and potentially a short route to being hired. This, what I'm about to show you next, is a closed form solution to calculating the Fibonacci number. Turns out there is an O of 1 solution to calculating the nth Fibonacci number. You just run this equation where phi of n is this, the golden ratio, which is 1.61803, et cetera, et cetera. So you might get bounded accuracy with this, but you can pretty quickly compute the nth Fibonacci number. And I had a question for that, but anyway. Let's give this one a run. This is another program which calculates the nth Fibonacci number and does it even more simply than our other versions, uses less memory and uses less space. And this is just an implementation of Binet's formula. I'm using math.h for my phi of n, I think. Oh no, I've defined phi here. Clang. We're up to fib4. Working pretty well. The only thing here is you'll notice I'm only using unsigned ints, so we're going to run out of space, but you could, out of memory for our numbers, but you could pretty easily change this to unsigned long longs. But arithmetic operations are not really O of 1. They're only O of 1 when we're dealing with small numbers, and even then, it's kind of glossing over what's actually happening inside the computer. If we were really going to dig in, we'd find that different arithmetic operations take different amounts of time, and they're not exactly O of 1. However, for most cases, it's a useful enough abstraction because most of the time, the time taken by the arithmetic operations is not going to be what dominates. However, it's always useful to remember it in the back of your head, so when you do come up with a confusing scenario or are in an interview situation, you can whip that out again. So what's the most efficient runtime we can get for this? So that already gave us a simple mathematical formula that we could calculate. That was a few steps. There was a square root. So there's a bit of involved calculation there for the computer. Our silicon's going to be crunching away doing that square root at least. Can anyone come up with a way to compute the third Fibonacci number really quickly? Does anyone know what the third Fibonacci number is? Let's assume we're starting at 1. 2. Okay, so can you remember 2 for me? What about the third Fibonacci number? A fourth Fibonacci number? 3. Tarish, can you remember the 3 for me? And now, what's the next Fibonacci number? 5. Can you remember the 5 for me? Okay, so now if I want to get back those Fibonacci numbers, if I want to get the third Fibonacci number, is there someone I can ask? Yeah, I can ask Yara right away. What about Tarish? What's the fourth Fibonacci number? And Albert? 5. Well, that was a lot faster than doing this square root calculation. We can just store a list of the Fibonacci numbers and ask for them back. Let's see what this would look like in our code in our very special Fib5. Here is a list of the Fibonacci numbers up to the maximum value that you can store in an unsigned long. And so why were we bothering with all this calculation when there are only like, I'm not sure exactly how many this is. Let's try fib5.c. I think we might be able to do 50. 80. Not in the table. Okay, so we're somewhere in that range. Go 90. Yeah, this is a bad way of doing it, but there we go. Fibonacci, the 90th Fibonacci number is the largest Fibonacci number that you're going to actually store in an unsigned long. And so this whole exercise that we were doing this entire class was completely ridiculous. If you're asked to compute the nth Fibonacci sequence in C in an interview setting, this is actually the fastest and most correct answer. There's no storing a giant table. There's no memoizing the previous recursive calls. There's no writing a fancy algorithm. Just literally write this down, and that is the fastest and most efficient way of calculating the nth Fibonacci number without using big nums in C. Which gives us our final takeaway for today. The real solution depends on the real problem. If you're operating C, if you're operating with unsigned longs, think about what you're doing before you're doing it. And if you're asked one of these stupid Fibonacci questions in an interview, give them Fib5 and watch their eyes roll. Thank you very much. Have a great weekend.